So we're just going to talk kind of quickly about nuclear power plants. Nuclear power is fascinating. So in nuclear power plants, you have to have some kind of nuclear material. So usually it's uranium-235, right? And some kind of a fissionable material. And then they are in these things called fuel rods. And these fuel rods kind of look like, I don't know, kind of like big pixie sticks, if you know what I'm talking about. That's kind of what the fuel rods look like. And in between the fuel rods are control rods. And the control rods, again, are going to absorb the neutrons. Because remember, when we split a nucleus, when we hit it with a high energy neutron, it breaks apart into two smaller nucleus. And then also 3 more neutrons break up. And so we have these control rods, which will absorb the neutrons. And so this is the way we can control how fast the reaction occurs. So if we need a lot of energy or a little bit of energy, depends on how much we use those control rods. And the rods are placed in a material that will slow down the electrons and, slow down the neutrons, and this is a moderator. Sometimes water, sometimes graphite, things that are good at absorbing neutrons. So here you can see is a nuclear reactor. So we have one of these in San Onofre. And the one in San Onofre is now offline, and I'll tell you why in just a second. Okay, so here's basically how the light water reactors work. And these are the ones we have in the United States. So you have your fuel rods. And again, these are about the size of like a large pixie stick. They're really not very big. They're like, the diameter is literally about that. They're not very big. And so here's your fuel rods right here. These are your fuel rods. And then these are the control rods. Now, depending on the reactor, sometimes the control rods come from the bottom. Sometimes the control rods come from the top. It just depends on the reactor. So let's say it's like 8 a.m. and everybody's getting up, going to school, right? Using their appliances. They'll take the control rods out, and then the reactor, the fuel rods, the neutrons are allowed to go hit more nuclei, right? Which splits more, releases more energy, right? But then like at noon, everybody's gone. Well, I mean, before the pandemic, right? Everybody's gone. And then they'll put the control rods in. And then the reaction can't happen as quickly because the neutrons are now being absorbed by these control rods. And this is how they can literally, they can either increase or decrease the amount of energy produced during the day just by lowering and raising these control rods. Now, there's an isolated pipe here. There's an isolated system. Do you see how this system right here? I'm just going to do this. This is isolated. So this is in direct contact with the nuclear material. It is it's isolated from anything else. So any nuclear material is isolated in that system. Now, what happens is this heat is enormous that's produced, and we're going to talk about that in just a couple minutes. And so what happens is the heat travels down this pipe, and then there's water here, which then produces steam. And the steam turns the turbine, which produces the electricity. Now, there's always extra steam, which I don't have a picture of here, but there's always extra steam. So if you've ever seen these giant towers, they look kind of like this. And they're these huge towers, and they just kind of tower over everything else. Those are where the excess steam is let out. So if you've ever seen like a big, huge tower when you drive by San Onofre and they're really tall, those are just to let the excess steam out. Now, once the steam comes in, the water comes out. This again, just erase on this. This is also isolated. So you see how this is also isolated? So therefore, the nuclear material that's in this isolated loop never gets into this isolated loop, right? Now, this is really important because this is why they shut down the facility at San Onofre. Because the seal, now, this is oversimplified. So a seal that they put the pipes together started cracking, right? So when they built San Onofre, someone who did a weld on one of these pipes did a bad job. and the weld started cracking. To repair this little crack here was so much money, they decided to shut it down instead because of weld cracks. So you can see nuclear energy, while it has incredible positive prospects, there's very large downsides at the same time. Repairing a crack wasn't even worth it, so they just closed the whole plant down. I mean, there was other factors also. People didn't like having a power plant in their backyard, but that's the reason they ended up closing it down, because it was too cost prohibitive to repair it. Okay, so just to show you again, so here's what it looks like when they put those control rods in, right? And so they can put these control rods in to absorb these neutrons. And again, this is how they control the amount of energy, right? By using these control rods. So that's just a little bit of basic how nuclear energy works. Now the question is, so we've been talking about fission, right? We talked about degradation, which we'll talk about, right, with our alpha, beta, gamma. And then we've been talking about fission. So the question we're going to talk about now is, where does the energy come from? So we know that when we split a uranium-235 nucleus, an enormous amount of energy is released. And here's where we're going to actually use in our calculations E equals mc squared. That's the long way. I'll also show you the short way in a minute. So each mole of uranium-235, each mole of uranium-235 nuclei that fissions produces about this much energy. This is an insane amount of energy. So if you think about like the most exothermic of all exothermic reactions we ever did, it was like 1,000 or 2,000, 3,000 kilojoules. This is so much more than any kind of chemical reaction we've ever done, right? 10 to the 6 joules, which is like 1,000 kilojoules, right? So this is way, way more energy. So what we're going to do now is we're going to use this equation to figure out how we do this. Like, where does the energy come from? Yeah, we get it. It makes energy, but where does it come from? It comes from this thing called a mass defect. So I'm going to explain what all these numbers are. So here's the statement that we're going to attempt to explain right now. And I'm going to attempt to write the math out so you can see it. So what we're going to do is we're going to take our reactants, right? Remember, right? The law of conservation of mass, matter cannot be created or destroyed. We're going to blow that up right now. We're going to use Einstein. So what we're going to do is we're going to take the mass here, and then we're going to compare it to the mass here, right? And the law of conservation of matter says matter cannot be created nor destroyed. Therefore, we should have the same mass of our reactants, same mass of our products, right? So let's add. So uranium-235, now we've got to keep all these digits because these numbers are going to be really small. So here is the mass of one uranium-235 atom. And again, AMU just means one atom. Here's the mass of one neutron. So our reactants weigh this much, right? Those are our reactants. Let's add our products. 1 barium 140, here's our mass. Krypton 93, here's our mass. 3 neutrons, here's our mass. So this is the mass of our products. You can see when I take the mass of my reactants minus the mass of my products, I lost mass, right? So we lost mass. This is not possible, right? But we did. Okay, this is the mass defect, right? And so the products have less mass than the reactants, right? And the missing mass is being converted in to energy. So the missing mass is being converted into energy via E equals mc squared, right? So that's what's happening to our missing mass. So let's use this missing mass, and I'm going to show you how this missing mass, I'm going to prove that that's the amount of energy you get per mole. Okay, I'm gonna try and write this really neatly. I thought I left myself enough room. I wrote these calculations down so I can hopefully remember. So this E equals mc squared, we call this the nuclear binding energy. It's the energy required to form the nucleus and also the energy required to break up the nucleus, right? And we'll talk more about this. This is our nuclear binding energy, the energy it takes to break the nucleus, which is exactly what we're doing with our uranium. Okay, and I know I have 235, I have 238 here. It's a mistake, I'll fix it. I just grabbed the wrong equation, but it works no matter what. Okay, so here I go with these numbers, which I calculated, and I do hope they are correct. Okay, so again, this mass in E equals mc squared, this is the mass that we lost. So I feel like you understand what these mean, so I'm going to just erase some of this. This is that mass we lost. C is the speed of light in a vacuum, 3 times 10 to the 8th, but of course we're going to use way more significant figures with it right here. Okay, so first thing, I need to put this in kilograms because the physics joules is like kilogram. So 1 joule in physics is like kilogram. Is it like meter squared second squared? If any physics people are over here, I'm pretty sure this is it. So this needs to get to kilograms. So I'm going to convert this to kilograms. And I'm going to use this conversion right here to do this. So 1 AMU, and I'm going to show you where these conversions come from in just a second, is, oh my gosh, 1.66054 times 10 to the 20 negative 27. By the way, you don't need to write this down unless you want to, because I'm going to show you a faster way to do it, but I just wanted to show you proving this was true. Okay. So I did these equations twice, so hopefully my numbers are right. 3.0702 times 10 to the negative 28th kilograms. Right, so that's the conversion I used to get this, and I got this in kilograms. Now I'm going to use Einstein. E equals mc squared. Here's my mass. 3.0702 times 10 to the negative 28th kilograms. And remember, this is just one atom we're talking about, times the speed of light, which it's 2.9979 times 10 to the 8th meters per second, but it's squared, right? And that gives us 2.7593 times 10 to the negative 11 joules, right? But again, this is one nucleus. We need to do a mole. So for 1 mole, we have 2.7593 times 10 to the negative 11th joules, 1 mole, right? But in 1 atom, and in 1 atom, right, there's, I don't even need to do my unit conversions, you get this. This is 1 atom times 6.02 times, actually, I need to be more precise with my numbers here, 6.021 times 10 to the 23rd. No, shoot, I love my computer. Let me see if I can fix this, sorry. Hold on, give me 1 second. It's like my computer really hates me. Okay, now I'm not going to be able to erase anything, but that's okay. Okay, to the 23rd, right? Atoms in 1 mole. And when you do this, you get 1.6617 times 10 to the 13th joules in 1 mole. Ta-da! That is where the energy comes from when we split the atom, right? So we figured it out. I'm gonna check one thing really fast. Okay. All right. So that's where our energy comes from. So now I'm going to show you, we'll talk more about this, but now we know where the energy comes from when we have a mole of our uranium. Now the mass defect and binding energy, you can pretty much do this with any atom. I just chose uranium there just so we could see it. So when a nucleus forms, some of the mass of the separate nucleons, remember those are the things in the nucleus, is converted to energy. The difference in the mass between the beginning, our reactants, and our products, that's the mass defect. So the energy that is released in the nucleus is called the binding energy. So in this case, E equals mc squared. That's what we call the binding energy, right? That's our binding energy. It's the energy released when the nucleus forms, which is also the energy it takes when we split it up. Okay. The greater the binding energy per nucleon, the more stable the nucleus is. So our most stable nuclei have the highest binding energies. So if you want to look at this is just the binding energy per nucleon. And per nucleon means per particle in the nucleus. So like a proton is a nucleon, a neutron is a nucleon, right? So per particle in the nucleus is what a nucleon is, just to review that. So you can see like our most stable nucleus, again, is right about here, right? Fe56 is about our most stable nucleus. So remember, the nuclear binding energy is the measure of stability of a nucleus, right? So the energy can be obtained by either breaking the nucleus up or combining it. So fission, breaking it up, fusion, combining it. And we're going to talk about fusion in a little bit. So now I'm going to show you an easier way to calculate the energy, right? I just showed you, I think is the most fun way, but there's an easier way to do it. We're going to do it per nucleon, which is a little bit better because it's more comparable to other nuclei. So we're going to calculate the mass defect and the nuclear binding energy per nucleon. Remember, nucleon, for our cases, that's just going to be protons and neutrons in mega electron volts. And I'm going to show you the conversion unit that we're going to use. And let's just do it for carbon-16, which is a radioactive isotope of carbon. And the mass of carbon-16 is this. So when we ask for mega electron volts, I'm going to show you the conversion we're going to use, which is one of them I gave you. This is the conversion we're going to use. So physicists like mega electron volts. We're kind of in the physics part of chemistry here, where physics and chemistry blur into one conglomerate. So we're going to use this one just because it makes your life so much easier, because 1 AMU is 931.5 mega electron volts, which makes our whole math a lot easier. I'll show you why. Okay, so when we do this, we need to know the mass of the protons and the mass of a neutron. So here's a mass of a proton and a mass of a neutron. So before now, we just said proton's about 1 and a neutron's about 1. Yeah, that's not going to work for our calculations. So we need to have like many more digits past our decimal point to figure this out. Okay, so we're going to find the mass defect in AMU. So we need to figure out the difference before. We're going to figure out the masses of our nucleus and our nucleon, including our proton and our electron. Then we're going to figure out the mass defect, and then we're going to use the mega electron volts to figure out the binding energy. Okay, so when we do this, there's going to be a difference. So remember, mass defect is saying, so this is going to be, we're not going to do this for like this fission, we're just going to do it for carbon-16. So you can see here, what it's saying is that when we add up the number of neutrons and the number of protons in carbon-16, this is what it should add up to, but it's not going to add up to that, right? That's the mass defect. Okay, so now here's how we do it. So if we look in carbon-16, right, carbon is 6, so therefore there's 6 protons and 10 neutrons. Remember this from Chem 219, Chem 209. So here's the mass of 1 proton. Here's the mass of a neutron. Let me just put this over here, carbon-16, just so you, in case you have forgotten how to do this. 10 neutrons. So here's our 10 neutrons. Here's our 6 protons. And I'm not going to write this out because my handwriting and all these numbers is not going to go well. And then here is the mass of carbon-16, right? So you can see this is our mass defect. So what we're going to do now is we're going to figure out the binding energy for this. And again, the conversion we're going to use, I did not put on here. Okay, I'm going to put your conversion up here. It's 1 AMU equals 931.5 mega electron volts. That's the conversion we're going to use. That's supposed to be 31. And I'm showing you how this one, it's a lot faster with your math. Okay, so here we go. It's our mass defect. And so now we're going to use this conversion. So you can see this is AMUs. So we're going to use this conversion to go from AMU to mega electron volt. So just like a little bit of baby stoichiometry right there. Right, so this is just use this conversion. Write this meter right here. And this is giving us our binding energy. But remember, this is the binding energy for carbon-16. We want to know what it is per nucleon. So you can look up here in the problem, per nucleon. Remember, the nucleon, for our purposes, it's a protons and our neutrons. Carbon-16 has 16 nucleons. So what we would do is we would just take our mega electron volts. Again, this we want to know per nucleon. We just divide it by 16. And that's going to give us our energy per nucleon, right? Because now we have mega electron volts per nucleon. So this is the binding energy for carbon-16. A little bit different than I did before, but much simpler. Okay, so now I'm going to have you try this on your own. Okay, so I want you to try this. I'm going to put the conversion unit you need. So 1 mega electron volt is 931.5 1 AMU mega electron volts. And you have the protons. I don't need to write the masses of the protons and neutrons. You already have those written down. So try this one, and then we'll see what we get. I'll give you a couple minutes to try this one, and then we'll go over it. Okay, so let's try this one. So we've got our mass of our protons, neutrons, and the mass of our isotope. Then we need to add them, find the difference, find the mass defect, the difference between, again, it's Fe, 56, right, with iron, 26. So we've got 30 neutrons and 26 protons. Add those and then subtract. So here's our 26 protons. Here's our 30 neutrons. And then here's the mass of Fe 56, which was given in the problem. So here is our mass defect. Okay, so that's our mass defect. Then we need to use this conversion I gave you, the 931 mega electron volts, right, in 1 AMU to get to our binding energy. So here's the conversion that I gave you, right? And then this, again, this is for the whole nucleus, but we want per nucleon. And remember, there are 56 nucleons, protons and neutrons, in our nucleus. So we just need to divide this number by 56. And there we go. That is the mass defect for our nucleus. Okay, so I'll let you write this down, and then I'm just going to show you the one right before it really quick. So you can see this one's 8.97, which is higher. .921, right? So the higher it is, the harder, the more energy it is, the harder it is, the more stable it is, right? So this is our most stable one, and per nucleon, we can compare it and we can see that this one is indeed 8.97 mega electron volt per nucleon, hence a more stable nucleus. Okay, so that is mass defect and binding energy. Now we've talked about fission, so we talked about decay, nuclear decay, and we talked about fission. Now we're going to spend a little bit of time talk about fusion. So nuclear fusion is the opposite of, well, pretty close to the opposite of fission. What it is, instead of splitting atoms, it's combining atoms. So it's combining two lighter atoms to make one heavier, stable nuclide. So fusion is common in our galaxy. The sun uses fusion of the hydrogen isotopes to make helium as a power source. So fusion, that's the energy of the sun. It requires enormous temperatures to occur, right? Because you're trying to combine two positive nuclei, right? Positive charges repel. We're trying to combine them in a fusion. So it's an enormous amount of energy that it needs to stay. It produces 10 times the energy per gram that fission does. So it provides way more energy than fission does. There's no radioactive byproducts when it comes to fusion. Unfortunately, the only way we've really gotten this to work is the hydrogen bomb. And the hydrogen bomb, so the hydrogen fusion bomb has 1,000 times the explosive force than the original fusion bombs. Right, so the nuclear bombs that we have are 1,000 times less powerful than our current hydrogen bombs. Tells you how crazy energetic these hydrogen bombs are. So here we have, this is called tritium. It's just a hydrogen 3 nucleus. This is called deuterium. So it uses tritium and deuterium. Those are just isotopes of hydrogen. And it makes it makes a higher mass helium, and then a neutron. But you can see here, there's no storage of the waste, right? The waste is not anywhere, it's not anywhere like the fission products where you have to store them for 1 billion years, right? When we looked at that uranium decay series. So again, the only real application we've got to make this work is in a hydrogen a hydrogen bomb. But to get the hydrogen bomb to work, it needs a really, really high temperature. The only way we can get the temperature high enough to get the hydrogen bomb to work is to include a small fission bomb inside the hydrogen bomb. So the fission bomb goes first to get the temperature high enough so we can create the fusion happening, and that releases 1,000 times more energy. So again, if we could get fusion to work as an actual energy source, this would be incredible. But we've never gotten a fusion reactor to be what's called net energy positive, meaning, so fusion reactors, there's a couple of them out there that don't really work yet, but we're working on it. Well, I'm not, but fusion scientists are working on it. So it takes more energy to get to the temperature that the fusion reaction needs to occur than you get from the fusion reaction itself. So that's what I mean, it's a net negative energy. So it takes more energy to get the reaction than you get from the reaction, which makes no practical sense at this point. So still working on it. Huge potential. We spent billions of dollars in research on our fusion reactors. So hopefully soon we'll get them to work, because if this works, then energy is no longer an issue for the world. Okay, so our last thing we're going to talk about today is artificial transmutation. And what this is, making new elements. And so what we do with artificial transmutation is we take high energy particles and we smash them into each other to make new nuclei. Literally, that's what they do. They make them go so fast and then they just smash them into each other. And so the particles, they could be, again, they could be moving, or they could have a particle hitting a stable particle. And it might be from another radionucleotide or a charged particle that's accelerated, all sorts of different things. The first one was made in the early 1900s. Rutherford made this one, and he made oxygen-17 bombarding with alpha rays from radium. So he took the alpha rays from radium and bombarded nitrogen-17 with it, and together made oxygen-17. Here's another one, CF244. This one is made by bombarding uranium-238 with carbon-12, right? This one's in a particle accelerator, which we'll talk about. And here's our new one. So you can make all sorts of things. So we have particle accelerators, linear accelerators, all sorts of accelerators. I'll show you some pictures of some. So again, what we're doing is we're just bombarding, crashing in one nucleus with another, creating new atoms. You can also hit them with neutrons. You can hit them with all sorts of things, different particles, different like alpha betas. You can hit them with all sorts of things. So there's linear accelerators and cyclotrons, and I'll show you these. So for example, technetium-97 is used by bombarding molybdenum-96 with deuterium. So here's this one here, that which they bombard it with the deuterium with the hydrogen to make new atoms. So if you look at your periodic table, all of the atoms, I know you can't see my periodic table. Maybe you can see it for a second. If I hold it up here, I'll just disappear. Yeah, see, I just disappear if I hold it up. All of them that have like the parentheses on there, where they don't have like decimal points on their masses, it's because we made them by smashing them into each other, right? So those are all man-made elements. So if you see any of those with like the little parentheses, those are, we made them by smashing them into smashing things together. We made elements. Now some of these elements last for like nanoseconds before they're gone. Some last a little bit longer. So here's a picture of some of the accelerators. Oh, I don't have a linear one. Well, the linear one looks like a line. Looks like a line. So here is, they have the linear one here. Here's this one here, Stanford. The cyclotrons are pretty cool. So the biggest one that there is, the biggest particle accelerator. So again, what these particle accelerators do is they use magnetic and electric fields to increase the speeds of the particles, and they do it in a vacuum because they can't have any other, like, think if there was air in there, they would continually hitting air molecules. So it has to be in a vacuum. So it's just those particles. And they are gigantic. So the biggest one is the LHC, the Large Hadron Collider. I think this is in like Geneva. Its diameter, 17 miles. 17-mile circle. It's the largest particle accelerator in the world. And so you can see like how big this was when they were constructing it. I was looking at pictures of it. It's kind of crazy. Which this was just a picture that I thought was pretty cool. But again, you can see when people walk in it, it's just like, it looks like they're walking in a mine. It's big. It's like 10 feet tall when you walk. You can see how tall it is when you walk in it. Okay. And again, it's 17 miles diameter. All right, so let's predict the daughter nuclide and write the nuclear equation for each of the following. So when we do this, you can kind of see it. It's just like nuclear equations. So in this case, we have nickel 60. I'm gonna try and write this right. So we have nickel 60 and nickel 28. It has to be balanced, and it's saying with a proton. So with a proton, that's our proton, and it makes cobalt 57. Cobalt is 27. And so when we look, well, what do we have? So we have 61 on this side, my mass number, right, is 61, and we have 57 over here. So we need 61 minus 57 is 4. This must have a 4 on top. Now I'm looking at the bottom numbers, 28 plus 1, 29 over here, 27 over here. We need another 2, right? It's an alpha particle, or you can say helium, right? So just like we were writing our nuclear equations before, you can just use these to figure it out. So let's do nitrogen 14 with carbon 12. Nitrogen 7. I don't know why these keep disappearing. With a neutron. So a neutron. It's going to make carbon 12. And now there's not always something formed, but sometimes there's something formed. So this is 15 over here and 12. So we need 3 on top. We have 7 over here and 6. So we need a 1 on the bottom. So 3, 1, that's a tritium nucleus, right? That's a tritium nucleus. Okay, try the last one, and then we'll go over it together. So try this last one, and then we'll go over it in just a minute. So we have CF250, which you really have to look at a periodic table for this one, right? It's number 98. It's hard for me to write down here on the bottom, plus boron 11, 11, 5, boron, produces 4 neutrons. So we have 4 neutrons, and then we just look at what do we have left, right? So when we do our math, 250 plus 11 is 4, so this is 257. Oh, that does not look like 257 to me. And then we have 98 plus 5, so that has to be 103. And 103 LR. So gotta have a periodic table for these. Definitely need a periodic table. Okay. So that is our transmutation. And I think we're gonna just finish there today because the next part's